this is the shaft, and here we have the impact loading to this one, and so this area equal to A, and this area n square A. Okay, we take one.
So is this talking about like different materials or?
The same materials here. So the same material, and say this is Young's modulus E, and the length is L over 2. Okay, we have one example here. So now for this case, we want to calculate the normal stress in this in the shaft in the bar. In each bar, okay. The same thing, the change in kinetic energy will become the total strain, and the change in the kinetic energy will go to the total strain and the strain energy for this system. And for this system, we have two portions here. And taking up that template, we know from, again, this is our template. So if we have the loading P, and if this is area and E, and the length is L, so the energy for this case is equal to QAE P squared times L. That is from the old, I pick up the formula. So we take up this template here. So for each portion, we simply plug in. And in this way, you can see for the impact loading, you must realize once this impact to the end here, they will produce an equivalent loading, just like we do the equivalence here. So that means in this formula, due to this the impact loading thing, you have to replace P by equivalent impact loading. Okay, so here, for example, let me pick up this one, and again, N is to indicate equivalent impact loading. We don't know that value yet, but we know they exist. Okay, so that one P squared, and for this case, the length is L over 2, and 2, and area is N squared A. E, and then for the right portion, that is the same impact loading. Why they are the same? Because that's propagated. And how to verify? You simply take the free body diagram on each cross section, right away you will see it. Okay, and then this is L over 2. The area, the 2 times area for this case is A and E. And so this one we simplify a little bit. Say when n equal to 2, then you say, I just actually plug a number here, so 6 AE and 5 PML square, PM square L, okay? This one is equal to this, 1/2 MV0 squared. So from here we can calculate first the PM will be equal to this number. 8, 5, A5, right? And then MV now and AE.
No, the
AE should be on the top. And L. Okay? Okay. And so therefore the loading will be equal to, right now for this case, the impact stress will be PM divided by A. And for this case, the sigma N will be equal to PM divided by NA. And here for our example, the N equal to 2, so we can calculate PM divided by 2A.
Oh, it's N squared
4. So this is 4. Okay. So once you have the PM, so basically we can calculate approximately. So that is for the application of the impact loading for this case. Probably next time I will talk about this one. But before we haven't done that yet. Okay, give me a few minutes. For the impact loading, you may ask what kind of real applications we might apply. And I don't know whether in the future you would have a chance to work in the automobile industry. I know that for those companies like Ford, they never be sending representatives to here interviewing students, never. But if you would have chance, and usually for the car, I think this is Texas style of the sedans. The grandpa style, right? They're very long, very huge, and if you hit them, his car is fine. Your car has a big dent, right? My advisor, PhD advisor, drove that to home, and I doubt that time he almost 70. I doubt how could he park his long car into the parking lot. It's a very huge one. I think that is a very good one, very good one. For this case, in terms of yaw vibrations, and you can see the wheel itself has elastic rubbers, and they have a suspension system here. And here has the engines, they have a suspension. So usually for automobile industry, they simulate for the car model is in terms of many combinations of the spring and damper. I just make one, okay? And for the spring and the damper representing the cushions. And to see how much more accurate you want to go forward, they just keep doing decomposing into the individual one. For each company, those model is a recipe, and that's a secret. And for different cars model, they have a different setting and parameters. Those ones can be obtained by experiment. Back to our problems, and usually they want to test the safety or reliability, and they will do a very famous testing is have a robot to drive the car and then directly hit the wall. And you see that once they hit the wall, the car will be something like this, and robot, the person will be something like falling into the windshield, right? And here for this case, this one, if you be able roughly, you might be able to simplify at the first stage the car into this simple system. And very likely this would be the, that would be, you know, if we look at the top of the view, this is a car, this is a wheel. have you seen the car, the bottom, the bed, the car bed, basically they make of the two, one or two beams. The beam is to support all these things. And this beam must be strong, okay, depends on the model. But that the beam, in addition to the engine, they take up a lot of the weight of the. So the car, once you hit that one, basically the two beams, you can approximate by this model. So at the very first stage, this model will provide you a certain upper or lower limit of certain impact loading informations. Okay, so that is the one direct applications for this one. Okay, and so that is for today. And remind me next time I will talk about the diving. You go to school, you go to the diving board and bump it, and then get in the water. That is the one.